temperature and the pressure globally here on Earth. So let's first take a look at the annual temperature patterns. Now we do see large-scale east to west temperature zones that occur throughout the course of the year, and this is due to the insolation variations. So if you take a look at this particular picture, if you will, animation, this is kind of reminiscent of your textbook pages 33, figure 215. What you'll see here is actually an animation of the what the Earth looks like as it goes from January to December. So notice at certain time periods, and if you you can always kind of take a look around February, December, January, you'll notice we have more blue up at the top. It's coming up. Notice it gets much colder in the winter time in the northern hemisphere, where in the summertime, then also in the northern hemisphere it gets a little bit warmer. Kind of goes quickly, you have to take a look. Now these are due to the insolation variations. So you can kind of see that east to west temperature zone varies as the year progresses. Now at the equator there's little seasonal difference. And here in Florida, you can kind of tell that. We really don't get a lot of the fall and the spring, like if we were to move up north. There's not a whole lot of that kind of stuff. We don't get the season changes, we don't get the leaves changing or anything like that. At higher latitudes, however, there are large seasonal differences, and this is due to decreased insolation and changes in day length. So as we move to higher latitudes, what we start to notice is that the day lengths get a little bit shorter, longer, depending upon the season, and that's due to the decreased insolation in certain areas. Now, do know that there is a time lag that occurs between when the sun is directly overhead and the period of maximum insolation. And I believe your textbook said about 2 months. I've seen about a month and a half before. So this basically means that even though the sun might be overhead in a particular month, we might not receive the maximum insolation from those particular things. And that's because of that time lag. So we might not get the full effects of that insolation. Now this is due to the fact that air is actually heated from below, not from above. So the first day of summer is not necessarily the warmest day of the year in many places. It's actually, we see a little bit later time where it actually becomes the hottest day. If you think about it, August tends to be one of the hottest months of the year in many places, a lot of the northern latitude areas, if you think of the United States. And this is due because of this fact that air is heated from below, not from above. Now the coolest period is usually after the winter solstice, and this is because the ground continues to lose heat after insolation resumes. So after the winter solstice, which is the shortest day of the year, you'll start to think that it should warm up after that. Well, that's not always true, and that's because the insolation hasn't gotten a chance to kind of warm the planet up a little bit yet. Now there's also a time lag greater over the oceans than land due to difference in heat capacities. Water has a higher heat capacity than land, meaning that it takes a long time for water to heat up. Land, it doesn't take much time. Now, along with temperature variations, we have pressure variations around the globe as well. Now, pressure here is measured in millibars, and I believe in the news you also see millibars an awful lot. Or you might see inches of mercury. Either one is correct, but in this textbook we use millibars. Now on a globe they're actually represented by something called isobars, and these are lines of equal pressure. So if you imagine at this picture, all of these lines that you see here, it's almost like connect the dots. Everywhere along this line will have the same pressure. Let's just say it's 1050 millibars. Every line on this line right here is going to have, let's say, 1060. So each line is kind of like a connect the dots. Those are called isobars. They're lines of equal pressure. So all these lines that I'm dragging my cursor on right now, all that has an equal equal pressure. Now maps use mean sea level, also abbreviated as MSL. And this eliminates the elevation in the pressure factor, because pressure will actually decrease as you go up in elevation, but we use mean sea level. So we're actually eliminating that elevation factor from this particular, when we talk about pressure. Now, overall, the mean sea level pressure is about 1013 millibars. However, there is a range from about 1060 to 940. So these aren't really high pressures or really low pressures. Remember, this is your mean pressure. Now, if we see a decline in pressure, we're going to have poor weather. If we see a rise in pressure, we have better weather. So we're not really interested in the number itself. We're more interested in seeing if there's a decline or a rise. That's really the important part that we want to understand and take away from pressure. We see a decline, we have poor weather. When there's a decline in pressure, we typically think about a hurricane. If we have a really low pressure, bad weather's coming. Maybe a hurricane's coming. If we have a rise in pressure, that's usually good weather. Nice clear skies, nice temperatures. It's just a very nice day. Now this is just a larger map of the particular the pressure variations throughout the year. And I have two for you. We have January and July. So I wanted just to point out to you, if you take a look, if you really get close into this, oops, sorry about that. If you really get close into this map, you're going to see lots of differences in Atlantic, the Pacific, and stuff like that. I'll show you some other examples as well. But on this particular map, you're actually able to see the isobars in more detail. So if you take a look, these are actually labeled for you. Like this one right here is 1020. The one above it, we have to find it, it's 1017. So these are all basically lines of equal pressure that kind of run around. Now we also see surface pressure belts, and these belts kind of run along the Earth in east-west patterns. And there's also a lot of difference between your northern hemisphere and your southern hemisphere. And here's why. Our northern hemisphere has much more land, so there's going to be a lot more seasonal change. So we're going to actually see a lot of different types of pressure going on in those locations. The southern hemisphere has much more water, so there's very little seasonal change. And the pressure belts are actually they're much more common and they're much more stable in this part of the world. Now this picture is just a general pressure wind belt map of the globe. And as we go through in detail through the text and the discussion in the notes, we're going to get into more detail. If you view figure 216 in your textbooks, page 34, there's another diagram that actually I really like. I was just not able to put into the presentation. So if we take a look specifically about some of these pressure belts, first let's take a look at what's known as the subtropical high pressure belt. You'll see this labeled STHP, subtropical high pressure belt. Now this is almost continuous in the southern hemisphere at about 30 degrees latitude. So in our little picture here, take a look at 30 degrees south, because we're going to be in the southern hemisphere. This subtropical high right here is pretty stable. It's going to be continuous right along 30 degrees south. Now the pressure generally is about 1026 millibars. And if we were to take a look at the northern hemisphere, at about the same latitude, 30 degrees latitude north, this is actually very discontinuous. We have a lot of land in these particular areas. So it's not always a subtropical high. We do see a lot of variation in this particular location. Our second pressure belt that is kind of important is called the Intertropical Convergence Zone. Now, you'll understand why it's called the convergence zone in the next slide. But this is an area of low pressure that sits over the equator, and it coincides with the zone of maximum insolation. So we're getting the most insolation on Earth at this particular location. The pressure generally is between 1008 and 1010 millibars. So it is going on the lower side. And we also see something in this area called the doldrums. Now these are area of pressure in which sailing ships have a hard time moving because there's not a whole lot of wind in these locations. So it's basically if you had a ship, a sailing ship with a sail, then chances are the ship would just stop. It would slow down because there's no wind to power it. So these are called the doldrums, and there's a lot of stories. I remember reading from social studies. There's a lot of stories that talk about the doldrums and where areas of water where the ships could not move. We also see subpolar lows. Now the subpolar lows typically are about 60 degrees latitude, both north and south. Now these have lower pressure than our subtropical high pressure belts, of course. However, there's a lot of variation. And your textbook describes a ton of variation that goes on in these subpolar lows. So in some cases, we could get high pressure, higher than what it's talking about here. Could get really low. It just depends upon what type of mass of air is sort of moving through it and what type of season. Now I'm going to use that same picture and I'm going to talk about surface wind belts. So this past picture was pressure belts. Now I'm going to talk about the wind belts. So we see these things called low latitude winds. And on this map, I'm actually pointing to them. They're called tropical easterlies. And these winds are typically between latitudes 10 degrees and 30 degrees. Both north and south. So we're going to see them right either above or below our ITCZ zone, our intertropical convergence zone. So we call them tropical easterlies because the flow of this wind travels from the east to the west. And that's how we name winds. We always name them from where they come to where they go. So if they're coming from the east, we call them easterlies. These are also called trade winds. On a lot of ships, this is kind of like your shipping lanes. This is a very nice area of location of ocean in which lots of ships like to travel because it's nice and easy to travel in these. Now we typically see warm, dry mornings in these locations with late afternoon showers, and this is due to continuous evaporation. Now that sounds kind of like Florida, doesn't it? We actually reside in this area of where the tropical easterlies come from. And a lot of our late afternoon showers, well, I shouldn't say a lot of them, but some of them are due to this. They're coming from the east. Because of where we're located in Florida, we also see a lot coming from the Gulf of Mexico. But it's basically because of this continuous evaporation in these particular areas. So once again, we see this intertropical convergence zone. And we see winds here. Actually, we don't see winds here because we already mentioned the doldrums. There's basically areas of zero wind. Now the winds do blow inward, and that causes the air to rise, which is then going to create low pressure. And we're going to talk more about this later, but low pressure winds tend to rise. So when we generate low pressure, the winds are going to blow towards each other. The air is going to rise, and that's where we're going to get low pressure. If we wanted to get high pressure, we'd actually have this separate way, the backwards way. The winds would blow outward, they're going to sink, and that causes high pressure. Now, rising air does release a lot of latent heat, and this stimulates convection. So what's going to start to happen is that this heat is going to rise, and it's going to actually start convecting, if that's a word. It's going to start convection happening in the atmosphere, and it's going to start to circulate some of that cooler air from the poles down towards the equator. I know I'm jumping ahead. We're going to learn about that soon, but that's sort of what's happening, and that's because of all that rising air causes a lot of latent heat. It's going to stimulate that convection. And then our last type of winds we're going to talk about here, these are our prevailing westerlies. So if they're called westerlies, They're coming from the west. And these westerlies tend to have latitudes between 35 degrees and 60 degrees, both north and south. So we find them both in the south here and up here in the north. Now, these don't really have the nice stable winds, kind of like the low latitude winds here, your tropical easterlies. Instead, we have winds that are rapidly changing, they're rapidly evolving, so we really don't know what we're going to expect in certain locations. So, kind of if we're talking about the westerlies, there really is no one particular wind per se. Now, to sort of wrap things up, I want you to remember that winds are due to the seasonal variations in the overhead sun. So this means that we might have different types of winds in different locations throughout the year because of the seasons, because of that insolation. Now, summer in the southern hemisphere actually means that it's winter in the northern hemisphere, and that's because of our tilt. This will increase the differences in polar and equatorial air. So it might have warmer air, cooler air, depending upon where that tilt is going. High-level westerlies are very strong in the northern hemisphere in winter. And we see this a lot of times in the wintertime. You can kind of see it on this map here. We actually get a lot of cold air coming from Canada, from the Arctic, and that comes directly down into the United States. We also see some of that also, not so much in this particular picture, because we don't see a lot of those westerly winds. Actually, we do. We see a lot of these winds coming out of the west, going boom, boom, like this. And that really dominates the northern hemisphere in the wintertime. You can kind of see it's a little bit different in the summertime. While these winds right here are coming from the west, the ones over here towards Asia and Europe, some are coming from the west, but some, notice, are coming actually from the north. So, and the east. We have a lot to talk about, of course, the different changes, but this will give you an idea of the temperature and the pressure as we move